Hello, everyone. Right, today we will be looking at adsorption isotherm fitting in Microsoft Excel. So in this experiment here, I have some raw data, which is for the adsorption of arsenic 5 or arsenate, adsorbing onto a suspension of titania, 1 gram per litre in 0.01 molar sodium chloride solution at a pH of 7. And here's a reference to the data sets. So first of all, in this Excel spreadsheet template here, we'll be fitting the Langmuir adsorption isotherm, firstly in the linear form, then the non-linear form, and then we'll look at the Freundlich adsorption isotherm. So the raw data I have is over here for the adsorption isotherm, and it looks a bit like this, the graph on the right. You will see that the first column is the equilibrium concentration of the adsorbate at the end of the reaction. Here I've used the units milligrams per litre, but you can easily use millimolar, molar, whatever unit you wish. And in the second column we have QE, which is the quantity of adsorbate that is adsorbed at equilibrium when the reaction has finished. So the Langmuir adsorption isotherm equation looks a bit like this. You have QE, the quantity of adsorbate adsorbed at equilibrium, equals Qmax, which is the maximum possible concentration of adsorbed adsorbate. If you occupied the total surface of your adsorbent, you can do a bit of reading about the Langmuir adsorption isotherm to understand this. Then we have KL, which is the Langmuir equilibrium constant, which represents how far to the right-hand side the reaction progresses. So this, if it's higher, then you have a greater affinity for adsorption. And you have C, which is the quantity of adsorbate that remains in solution at equilibrium. So this is the Langmuir adsorption isotherm equation. And how can we fit it? So firstly, we'll look at linear fitting. So this is my raw data here. And one form of linearized Langmuir adsorption isotherm is this equation here, CE over QE equals 1 divided by Q max times CE plus 1 divided by Q max plus multiplied by KL. So this is a linearized equation because it takes the form y equals mx plus c, where y equals CE divided by QE and x equals CE here. So if we rearrange the equation, we can create this linear plot here, where we have CE, which is our value of x, CE divided by QE, which is our value of y. And you can see that this data here, which was originally curved, is now linear in a straight line like this. And we can fit a simple linear regression to it. So if you have your data like this, you simply left-click, right-click Format Data Series. Oh no, sorry. Right-click, Add Trend Line, and you'll get a line up like this. That's your linear trend line, and you can display the equation and the R-squared value. If the R-squared value is greater, closer to 1, then it's a better quality fit. Right. However, normally we prefer to use the LINEST formula in Microsoft Excel because that can give us a little bit more information. It can give us some statistics as well. Not just these numbers here, but it can also give us an uncertainty for each number. So here I've used the LINEST formula with my y-axis data and my x-axis data. And if I put true and true here, this first true puts the linear regression through 0, 0. And the second true displays statistics as well. So you can see I have a lot of statistics here. If you want to use the LINEST formula and get this extra data, you need to create an array. So you select 2 by 6 array of cells here, and you put equals LINEST brackets known y values, so that's all the y values here, known x values, which is all the x values here, and then I'm going to put true, so it goes through the origin, and true, so it gives me statistics. And then you need to hold Control, hold Shift, and then push Enter, and then you will get your table here. So this is the output of the LINEST function in Microsoft Excel. And you can see that the first two numbers are the same that we get from just clicking and adding a trend line this way. So 0.1 is our value of M, 0.13 is our value of C. The two numbers underneath this are the standard errors. So this cell here is the standard error in M. This cell here is the standard error in C. And then this number here is the R squared value, which should be the same as the R squared value here. And the other statistics, we don't need to worry about it. So from this linearized form of Langmuir adsorption isotherm, I can use these relationships here to convert my M values and C values into values of Qmax, which is the maximum adsorption capacity of your adsorbent according to the Langmuir adsorption isotherm model, and to get this value of KL, which is the Langmuir adsorption constant. Yeah. So we can go and model it as well. Okay, so here in this modeling column, we simply have this expression here, which is Langmuir adsorption isotherm, and we're putting in the KL values, the Qmax values, and CE. And we can see what it looks like on this graph here. So let's add the model. And you can see that this is the output we get when we determine our adsorption isotherm parameters using linearized Langmuir adsorption isotherm equation. However, a lot of people now recommend that instead we use non-linear fitting because we might get a better quality of fit when we look at the data in this form. So in linear Langmuir adsorption isotherm fitting, we try and minimize the difference between the model, which is this dashed line, and the experimental data, which are these solid data points, in this form here with this interesting y-axis value. However, maybe it's better if we actually fit the data to y-axis data in the original QE form. I'll show you what that looks like over here. So in the Langmuir nonlinear fitting, we have the same raw data, we have the same adsorption isotherm equation, but we're instead going to fit our model directly to this graph here, in this form here. So we're not going to linearize the equation. And it's a little bit harder because we're going to have to use Microsoft Excel's data solver function. So, okay, so how does this work? So when we fit the linearized Langmuir adsorption isotherm, Microsoft Excel is going to alter the slope and y-intercept of this line to try and achieve the best R squared value here. We're going to do the same thing to try and get the best R squared value, but we're going to have to use a function called data solver to manipulate the two parameters until we get the best R squared value. So this is the experimental data, and we want to model it using this Langmuir adsorption isotherm equation and calculate the R squared value. So if the R squared value is closer to 1, it means our model is doing a good job. So R squared, the way we calculate it is simply 1 divided by the sum of squared differences between model and experiment divided by the sum of squared differences between model and the average value of QE. So here we are looking at the difference between each QE value and the average value of QE, and we're squaring it. Okay, so we square all these and we sum it, and that's our denominator when we calculate R squared. And we do the same with the model. So here I've just put 8 and 2. These are guess values for what Qmax could be and what KL could be. And we do the same over here. So we are, can I zoom in? No. So we are subtracting the model's value of QE from the experimental value of QE, and we're squaring it. And then we sum it down here. And then the R squared equals 1 divided by the sum of the squared differences with the model divided by the sum of squared differences with the average. Okay, so that gives us an R squared value here. So here's our data set. We can add the model. So these are two parameters that we just guessed at. So we guessed that Qmax was 8 and KL was 2, you can see that here our adsorption finishes at about 8 for QE in milligrams per gram. If we change this number to 9, we're going to see, okay, it gets a bit higher. If we change it to 10, we're going to see that the model line goes a bit higher. But we don't just want to do that ourselves, just play around with numbers until we get there. We want to use Microsoft Excel's data solver function. And when you open up Excel on a new computer, you won't normally have this function. So the way to find that is to go File, Options, Add-ins, and then there's a Manage section down here. You will click Go, and it will give you an option of add-ins, and you'll select the solver add-in. And then this button here will appear. So we click the solver function, and what we want to do is we want to take our R-squared value, which is currently 0.65, and we want to maximize it as close to 1 as we can. And we're going to do that by manipulating these two cells here. And normally we don't need to change any other parameters here. So we click solve, and what we're going to see is, oh, that was very fast. Okay, solver has converged to the current solution. So you can see the value of 10 for Qmax has changed to 9.2, and KL has increased to 1.5. When you have a more complicated problem, the solver can often take a few seconds or even a few minutes to run, depending on how big your problem is. Okay, so we OK that and we keep those values. And you can see the line has changed a little bit now, and it should give us a better fit. Okay, so that's the Langmuir adsorption isotherm. You can look up the theory of that. So that's when you have a limited number of surface sites for adsorption. In contrast, the Freundlich adsorption isotherm doesn't have a limited number of adsorption sites. So adsorption can theoretically increase to infinity. And we've got a different equation. So we've got a different Freundlich adsorption isotherm equation, QE equals KF, which is the Freundlich equilibrium constant, times CE, which is the aqueous equilibrium concentration of adsorbate, to the power of 1 divided by n, where n is our second fitting parameter. In the Freundlich adsorption isotherm equation, we have a different linearised form. So the linearised equation is different to the linearised Langmuir equation. So we have the natural log of QE divided by equals 1 divided by n times the natural log of CE plus log KF. And in the form y equals mx plus c, we can obtain n because it's 1 divided by m, and kf because it's the exponential of c. So you can see that we've plotted the data here now with different x and y axes versus the Langmuir adsorption isotherm. So we have the natural log of CE on the x-axis and the natural log of QE on the y-axis. Again, we can fit it with the linear regression, and we get y equals mx plus c and an r-squared value. One important thing that a lot of people do wrong is they compare the r-squared values in the linearised Freundlich adsorption isotherm with the r-squared values in the linearised Langmuir adsorption isotherm. And you can't compare these. You can't say the Freundlich model is better than the Langmuir model or vice versa on the basis of how good these r-squared values are, because the axes are completely different. The units are completely different. Okay, so don't compare the models on the basis of r-squared in the linearized form, but you can compare how good the models are based on the r-squared value in the non-linear form. Okay, so yeah, then we have a spreadsheet tab where we have the non-linear fitting of the Freundlich adsorption isotherm. Okay, so again, we can put the model in, this time using the Freundlich adsorption isotherm equation over here. And we're going to calculate the r-squared value. Okay, and we're going to take a guess at what our constants can be. So let's look at the model, apply. Okay, so really bad guess right now. Okay, so we're going to change these, see if we get a bit better. Okay, so taking a guess, it gets a little bit closer. And when you're ready, when you're in for a rough ballpark figure, you can run the solver function again. So here we're going to try and improve the R squared value by changing the values of n and kf. So let's click that. And again, it was pretty fast. So it manipulated these values and it gave us 3.2 and 7.6. And you can see that the fit is fairly good here in the Freundlich adsorption isotherm. I should mention that this is a different experimental data set for the Freundlich adsorption isotherm. We're looking at arsenic-free arsenite. So, yeah. Okay, so we've looked at both the linear and the non-linear fitting of the adsorption isotherms. Why does it matter whether you use linear or non-linear fitting? Well, it matters because you're going to get different quality of fits. So in the linear adsorption isotherm models, you're trying to improve R squared, but you have different y-axes and sometimes x-axes versus the non-linear adsorption isotherm fitting. So you should always get a higher R squared value, so a better quality of fit, when you use the non-linear adsorption isotherm fitting using Excel's data solver function. So you can see the R squared value is improved and the R squared value is improved. But overall, the models look roughly similar. Yeah, and why does that matter? So if you look at the linearized form of the Langmuir adsorption isotherm equation, you will normally get this kind of diagonal line like this. And when you fit the data to this linearized form, you're going to weight the final data points on the right-hand side more heavily than the data points in the middle and on the left-hand side. And this means that your adsorption isotherm model is going to try and overfit the final data points and maybe underfit data points in the middle and on the left-hand side. That's why the linearized form of the adsorption isotherm in this data set has fit the final data points perfectly, whereas the non-linear adsorption isotherm has tried to fit the entire data set. Not sure. So the key difference between linearized and non-linear adsorption isotherm fitting is how the data is weighted when it is fit. Which data points are most important when optimizing the model? Most studies will use linearized adsorption isotherms because it's the quickest and easiest way of obtaining your adsorption isotherm parameters, and it normally works pretty well. So here we have the linearized form of the Langmuir adsorption isotherm equation. The problem here is that these data points are to some extent more important when we fit the model in the linearized way than data points in the middle or down the bottom. And why is that? So you can see that this data point here, if we move it down, I don't know, X amount, we're going to start to see that the linear regression is going to change quite quickly. Okay, linear regression will be very sensitive to this data point here. In contrast, if we decrease the central points by the same amount, the linear regression kind of isn't going to change that much. It's going to be a lot less sensitive to this data point. In contrast, when we look at the nonlinear form of the Langmuir adsorption isotherm equation, when we move the same data points by the same amount, they're going to have kind of a more even effect on the quality of the fit. So if we move this final data point down, the model is not going to change too much. It will look a bit like this. If we move this data point down, again, it's going to be quite similar. It's just going to move down a little bit. Okay, it will sort of be an average of these data points here. Yeah, so that's one thing to bear in mind. Even though our adsorption isotherm experimental data has plateaued here, it's reached a flat constant level. In the linear plot, we're still going to have a slope, and it's going to go up and up and up forever. And that just means that the weighting when you fit the model is going to be a little bit different whether you use nonlinear or linearized adsorption isotherm equation. So one important thing to bear in mind when you are using the solver function of Microsoft Excel is that it won't always give you the best solution to your problem. It depends on the initial conditions you put in. The way the algorithm works, the solver algorithm, is that you tell it which parameters you would like it to change. For the Langmuir adsorption isotherm, we told it please change KL and Qmax. For the Freundlich adsorption isotherm, we told it please change KF and N. So Excel is going to manipulate these values, and it's going to look at what happens to the target value, which for us was R squared. We asked it to maximize R squared. And we need to put a guess value in for Microsoft Excel to start working with. So the way it's going to work is that Microsoft Excel's data solver function, we're going to give it an initial guess. Maybe we choose parameters that put us at this R squared value here. And it's going to move them around. So maybe it increases parameter 1 a bit, and maybe it tries decreasing parameter 2 a little bit. And we're going to see which way we go. Okay. And Excel data solver function is going to have multiple iterations. It's going to slowly change the parameters in incremental steps to try and improve the R squared value. So if it moves up to the right, it's going to see that R squared is improving, and it's going to keep these parameters, and it's going to increase them a bit more. Eventually, we will get to this point here, which is a local maxima point. So when Excel tries to change the parameters more, it's actually going to make the R squared value worse. So it's not going to like this position here. So Microsoft Excel's data solver function would converge on this value here, and it would tell you that the optimal solution is to have your parameters at this value here. It will think that this is the best R squared value, when in reality, our best R squared value is here. The same thing, if we start over here, position number 2, we're going to Excel's data solver function will move in this direction. It will come up here, and it will get stuck here on a solution which is pretty good, but it's not the best. So you have to bear in mind that you're only going to get the best results if you give it initial conditions which are already okay-ish. So you need to take a good guess before you start the data solver.